Hi everyone and welcome to our final presentation, Income Classification using SparkML, a predictive analysis of census data. This project was completed by Akshar Kumari, Krishnaburo, Dipanjan Ghosh, and myself, Xavier Singletary. In the next few minutes, we'll talk you through how we use Spark to clean data, analyze patterns, and build models that predict income categories. We use Databricks Community Edition with Apache Spark to build a scalable distributed pipeline. A key part of our setup was reproducibility. We set a random seed and maintain a consistent Spark session across the team to ensure reliable results and a smooth collaboration. This environment allowed us to manage memory efficiently and run large-scale data processing with ease. The goal of our project was to predict whether an individual earns more or less than $50,000 annually. To do this, we use Apache Spark's MLlib to train models on demographic data such as education, marital status, occupation, and work hours. We also aim to uncover which of these socioeconomic factors were the most predictive of income outcomes. We use the adult census data from the UCI repository, originally based on 1994 U.S. Census data. It includes over 40,000 observations and 15 attributes, both categorical and numerical. The target variable was income, which we split into two classes, less than or equal to 50K and greater than 50K. The mixed data types made pre-processing an essential step before modeling. We encountered several common real-world data problems. Many entries had missing values, marked by question marks. There were formatting inconsistencies like little extra spaces and stray punctuation. Some categories, such as without pay, were rare and ambiguous. Additionally, null indicators weren't standardized, so we needed to manually define what constituted a missing or unusable entry. To clean a dataset, we replaced question marks with nulls and removed incomplete records. We trimmed and normalized string fields and removed symbols from categorical values. Low frequency and unclear word class entries were excluded. Lastly, we cast numeric features into the correct formats to ensure Spark could process them during feature engineering and modeling.
After cleaning the data, we engineered features for machine learning by first applying string indexer to categorical variables. To avoid misleading ordinal relationships, we then used one hot encoder to create binary columns. Next, vector assembler merged all features into a single vector, and the income label was indexed into binary format for classification. This process flow diagram shows our end-to-end pipeline. Starting with raw census data, we perform data cleaning, feature engineering like indexing, encoding, and vectorizing, model training with SparkML, and model evaluation to select the best algorithm, ensuring consistency and scalability throughout. This slide reflects that we use Spark SQL to explore large datasets efficiently, creating summary tables without manual aggregation. Using Spark SQL, we grouped individuals by age brackets and marital status, revealing that those aged between 30 to 49 had the highest marriage rates. This insight was key, as marital status correlated strongly with higher income and became a valuable predictive feature. Our second SQL analysis examined work class distribution for individuals aged 20 plus, excluding without pay and never worked categories. We found private sector jobs dominated across age groups, reinforcing work class as a strong predictor of income due to its link to earning potential. In our third SQL analysis, we used window functions to estimate median age by education level and occupation, and it concluded that higher education levels such as bachelor's and master's aligned with older median ages, reflecting extended study periods before workforce entry and potentially higher later earnings.
After completing our initial SQL analysis, we visualize the distribution of income categories within the dataset. As shown here, there is a significant class imbalance with the majority of individuals earning $50,000 or less per year. Accounting for this imbalance was important for us to understand the potential model behavior and evaluation challenges later on. Next, we implemented a variety of machine learning models using SparkML pipelines. Our goal was to test both linear models like logistic regression and more complex nonlinear models like random forest and gradient boosted trees, with the same goal of predicting whether an individual's income was less than or equal to $50,000 or greater. Our first model was logistic regression, a standard linear classifier used for binary classification tasks. We tried to tune the default hyperparameters of the baseline logistic model to come up with a tuned version. But despite tuning, the performance remained very close to the baseline. The baseline logistic regression model achieved a testing accuracy of 84.93%, while the tuned version dropped to 84.62%. This suggested that the predictive power of a simple linear model was limited for this dataset. Our second model was a decision tree classifier, which offers the ability to handle complex nonlinear relationships between features and the target variable. To prevent overfitting, we restricted the maximum depth of the tree to 7, which provided a balance between model complexity and generalization. The decision tree achieved a training accuracy of 84.67% and slightly lower testing accuracy of 83.71%, indicating minor overfitting. Our third model was a random forest classifier, which builds an ensemble of multiple decision trees. Each tree is trained on a random subset of data and features, and the forest aggregates all the tree's predictions to make a final decision. This reduces the variance and overfitting significantly. The random forest model achieved a training accuracy of 86.09% and a testing accuracy of 85%, clearly outperforming both logistic regression and the single decision tree model.
Our best performing model was gradient boosted trees. Unlike random forest, GBT builds trees sequentially, learning from the errors of previous trees. It uses gradient descent to minimize prediction error. GBT achieved a training accuracy of 86.92% and a testing accuracy of 86.14%, showing not just high accuracy but also excellent generalization on new data. This table shows how each model performed on training and testing sets. Most models generalize well, especially GBT, which maintained consistent performance. Decision trees showed a slight overfitting with a drop from 84.67% to 83.71%. The neural network underfit the data with both training and testing accuracy below 80%, likely due to limited tuning or complexity. Across all models, GBT stood out with the highest accuracy. Logistic regression and random forest also showed strong, stable performance, making them reliable fallback options. In contrast, the neural network performed poorly, confirming the simpler models often outperform deeper ones without extensive tuning or data volume. We faced several real-world data issues. Missing values were replaced or dropped to maintain integrity, and inconsistent formatting required trimming and cleaning text fields. Class imbalance was acknowledged during model evaluation, and we kept training time manageable by limiting tree depth and optimizing SQL operations in Databricks. In conclusion, gradient boosted trees was the best model in both performance and generalization. Its ability to balance complexity and accuracy made it ideal for structured data like this. Cleaning, pre-processing, and careful feature selection contributed to that success. Moving forward, we could improve results with more hyperparameter tuning and by addressing class imbalance.